Hello, today I'll be discussing new challenges for CMB experiments, a case study in the dark sector. This is some recent work done with myself and some collaborators at IAP, in which we explored some of the challenges that we face with using contemporary CMB datasets to try and constrain model parameters for beyond LambdaCDM model extensions. So in our work, this is with Ali Rida Khalife and Sylvia Gelli, we tackled here some of these models as example case studies to sort of illustrate the kinds of challenges that these analyses face if you want to use new CMB datasets to constrain these models. What kinds of difficulties do we have? So this is not meant to be sort of a exhaustive constraints on all of these models, or even on the models that we did choose. We didn't explore every corner of the parameter space. This is really meant to more serve as an illustrative example. So the first category of models that we consider is the scattering of dark matter with baryons. Now, as far as how this affects the CMB, you can parameterize this with just a few parameters that capture this effect, and this is independent of the details of the underlying particle theory that actually generates this interaction. So you need to know the velocity dependence of the scattering, the overall amplitude of the cross-section, the mass of the dark matter particles, and what fraction of the dark matter is participating in this interaction. And this parameterization is already implemented in the publicly available Boltzmann solver class. So turning on this interaction has two main effects on the CMB. The first is a slight shifting of the acoustic peaks, and the second is a suppression of power on small scales as the scattering cross-section increases in magnitude. And in particular, as the error bars of our CMB datasets improve on these smaller scales, there are corrections to the matter power spectrum beyond the linear theory, which become increasingly relevant as your data becomes more sensitive at these small scales. So there are some codes available, including implemented within the commonly used Boltzmann solvers class and CAM, things like HaloFit and HMCode, which can compute these nonlinear corrections to the matter power and subsequently their effect on the CMB lensing power. However, these codes are calibrated from n-body simulations, which do not include all of these fancy beyond LambdaCDM extended models like dark matter interactions with baryons or other things. And it turns out if you just sort of turn on this interaction and ask these codes to give you an output for the nonlinear matter power, they're just not numerically stable because this is not what they've been calibrated to do. So we also observed similar behavior for the other class of models, which I'll shortly discuss. And so we particularly caution people to take care with these settings when using these Boltzmann codes, and make sure that you are setting these options appropriately. The second class of models that we consider is dark matter particles, which interact with dark radiation, also in the dark sector. The effect of this interaction on the CMB can also be parameterized with a handful of parameters. In particular here, we use the ethos formalism, which is also implemented in the class Boltzmann solver. So we need to know the amount of dark radiation, the amplitude of this interaction rate between the dark matter and the dark radiation, the temperature dependence of this interaction, and again, we need to know the mass of the dark matter and what fraction of it actually interacts. And furthermore, the nature of the dark radiation could be either free streaming or self-interacting. For the particular parts of parameter space that we explore in this paper, we are considering free streaming dark radiation. So this also affects the CMB power spectrum, both the primary CMB and the lensing power. There is a very slight shifting of the acoustic peaks for the interaction strengths chosen here. You almost can't see it on the plot. The sort of big noticeable effect is the suppression of small scale power, in particular in the lensing power. And again, this is happening at small scales where the nonlinear corrections to the matter power are particularly important. So what can we do if we would like to run some parameter inference for the extended models discussed here, for the parameters of those models, using our CMB observations? Well, as discussed a few slides ago, the nonlinear codes like HaloFit and HMCode are simply not calibrated to capture these effects, and furthermore, their outputs are just not stable if you try to force that. One choice that's sometimes made in analyses to study extended models using CMB data, but if you don't have a theoretical nonlinear prescription available, is to simply use the linear theory only. And for data sets that are not very sensitive in regimes where the nonlinear theory matters, this approximation can be okay to make that choice. But potentially you are incurring some bias in the central values of parameters that you're inferring from your data, in particular if these data sets become more sensitive to the nonlinear regime. So on the right, we have an example. The upper panel just shows you the relative impact of including the nonlinear theory can be an order 20% effect at a lensing multipole of about 1,000. And in the bottom panel, we show the effect on the lensing power of dark matter baryon scattering. So the scattering suppresses the power at small scales. So if you perform your analysis, running your theory code with just the linear theory, the actual data that you're comparing to, which would be more like the pink curve, is going to have slightly higher power. So your fit will attempt to decrease the scattering cross-section, resulting in higher lensing power, which means it'll prefer cross-sections closer to zero and even potentially miss detection, even if your data is actually sensitive enough to detect whatever that cross-section is. So as we said, one potential workaround is to simply use linear theory only and incur some bias. So for LambdaCDM, we can use these existing HaloFit and HMCode prescriptions and quantify exactly what that bias is. For extended models, well, if we had working codes for those, we could simply do the analysis, but even to quantify exactly what these biases are, we would need output of n-body simulations, which was beyond the scope of this particular paper. Since our work came out, there has been a recent very cool paper about n-body simulations of dark matter baryon interactions, which I refer to here. And yeah, we also point out that of course, there are degeneracies between LambdaCDM and some of these other extended model parameters. So any issues of biasing one parameter or another are interrelated. At the time of doing our analysis, there were a few data sets available which had not yet been applied to some of these interactions, including the SPT 3G 2018 data for both primary CMB and lensing, and the ACT-DR6 lensing data. This was before the release of the ACT-DR6 temperature and polarization data. So for Planck datasets and the SBT3G 2018 data, we actually quantified what these parameter biases are if you include the nonlinear corrections to the matter power spectrum, and if you neglect these corrections entirely and use the linear theory only. Now, in the right panel for Planck and Planck lensing data for that combination, we found shifts in parameter values on the order of 0.2 sigma. For the SBT3G temperature and polarization data combined with the SBT3G lensing, we found parameter shifts as large as 0.6 sigma when the nonlinear theory is neglected. For the ACT-DR6 lensing dataset, we did not run our own chains to quantify this. There was already a very nice figure in their paper, which shows similar order of magnitude of parameter shifts if you use only the linear theory. So here are our results for dark matter baryon scattering. As a conservative analysis choice, I should add on the previous slide, so these were showing the shifts, including primary and lensing data. We checked this using primary temperature and polarization data only and found the shifts to be smaller, and thus we consider them acceptable to do the analysis, just using the primary CMB subset of the data with linear theory. So as a conservative choice, that is what we did. So in this table, P is Planck T&E data, B is BAO data, S is the SBT temperature and polarization, and A is ACT temperature and polarization. And when we add the SBT3G data to Planck, which had not previously been combined, we find a small but noticeable improvement in the error bars. And we furthermore find that in the cases that we considered, the constraints from the SBT data are consistent with zero scattering cross-section. So this is what we can do with some limited subset of our data. There will be new data releases coming in the near future. We ran some Fisher forecasts to simply quantify approximately how much of an improvement in the error bars you could expect if, for example, you can utilize your lensing data. So for the upcoming SBT3G dataset from the 2019 and 2020 observations, if you can include lensing in that dataset, that's an order 50% improvement in your constraining power. And again, it's been a few months since our paper came out. In the meantime, there has been some excellent, more recent results. Again, I link them here. There's a paper on bounds on velocity-dependent dark matter baryon scattering from large-scale structure, and the ACT-DR6 constraints on extended cosmological models also include dark matter baryon scattering. And in fact, they use a variation of the class PT code, perturbation theory, which does in fact have this interaction included and can thus estimate the nonlinear contribution to the matter power spectrum. For dark matter, dark radiation interactions, if we make the conservative analysis choice to use only the primary CMB data, which is less sensitive to whether you use the linear theory or the nonlinear theory, we find that the parameters of this model are basically unconstrained. So to check the constraining power of the lensing data, we tried running the chains with the lensing data included, and then we do get limits on these model parameters. So that tells you that The constraining power of this lensing data is very important, perhaps unsurprising if you recall from the plot a few slides ago, showing the effect of this interaction. It was primarily seen at the small scales of the CMB lensing power. We do caution, however, that the results presented in these figures and tables are to be taken with caution. We have, in the case of including the lensing data, we've used data which is sensitive to the nonlinear corrections, but we've done the fits using theory code output, which is computed only with the linear theory. This is mainly meant to illustrate the fact that there is a great deal of constraining power in the lensing data, not so much the exact numerical value of the constraint that you get. In conclusion, we have some very exciting data, which, if anything, is starting to get a little bit ahead of the theoretical tools that we have available. We caution the use of current and especially upcoming CMB lensing data in constraining these beyond LambdaCDM models if we don't have a reliable way to estimate nonlinear corrections to the matter power spectrum. So one strategy that can be used is to simply ignore these terms, but this does result in order 0.6 sigma shifts in parameters for the current CMB datasets that we examined in this paper. For dark matter baryon scattering, we've provided some constraints combining Planck with the SPT 3G 2018 primary CMB data showing a small improvement, but we did not include all of the released data that we had at our disposal at that time. For SPT 3G datasets in particular, we forecast up to 50% improvement in their constraining power if you can include the lensing data. For dark matter interacting with dark radiation, we find the model parameters are unconstrained using only primary CMB data, and we get meaningful constraints only if we can include the lensing data, which is sensitive to the nonlinear corrections. Of course, future CMB datasets will only be mapping the CMB with better and better precision. So in order to test all of this very interesting and very cool BSM phenomenology, we do need to continue working to improve our theoretical tools. Otherwise, we can make choices to impose various cuts on our data. Thank you.